Welcome to the first video in our thermal chemistry series, in which we will explore the energy changes that occur in chemical reactions and how reactions either produce or consume energy. For our first phenomenon, we're going to be taking a detailed look at water and trying to look at why water is one of the few compounds that exists naturally on Earth in all three of the different states of matter. So we know that water exists as ice as long as the temperature is below 0 degrees Celsius, which is freezing temperature, and we know that water exists in its gas form as water vapor as long as the temperature is greater than 100 degrees Celsius, and of course we know that 70% of Earth's surface is liquid water as long as our temperature is between boiling and freezing. So why does water do this, and why don't we see this phenomenon with more compounds that exist on Earth? Well, the primary reason why is that water is a very strongly polar molecule. We know water is polar because oxygen has two lone pairs of electrons, while hydrogen is none, thus creating a distribution of negative charge from oxygen's lone pairs on one side of the molecule. Additionally, because oxygen has a much higher electronegativity than each of the hydrogen atoms do, oxygen is going to pull the electrons in its bonds with hydrogen closer to itself, causing oxygen to accumulate even more negative charge, while hydrogen is going to accumulate positive charge as electrons move away from it. Because of the fact that every water molecule has this type of charge distribution, that means the negative side on the oxygen side of water can attract to the positively charged hydrogens in order to produce what we call hydrogen bonds, as you should have learned about in the molecular polarity unit. Hydrogen bonds are the key to understanding how water has this such great ability to exist in three different states of matter, but also to resist temperature change. So we know that in order to change the state of matter with water, you either need to add heat. For example, if we wanted to evaporate liquid water, you would need to increase the temperature by adding heat, or you would need to remove heat. Again, if you wanted liquid water to freeze, you would need to decrease the temperature by removing heat. Now, water's resistance to temperature change we can summarize in one key term that will be key to understanding the first part of the thermal chemistry unit, and that is what we call specific heat capacity, which we will represent with the variable C. We will take a look at the formula for where this comes from. So specific heat capacity as a definition is the amount of heat measured in joules, which is the standard international unit used to measure energy change, the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius, although often, remember, in chemistry we use the Kelvin scale rather than the Celsius scale, but the order of magnitude, 1 degree Celsius, is the same temperature change as 1 degree Kelvin. So as mentioned before, we represent specific heat capacity with the variable C, and if we try to put the units for specific heat capacity into a measurement, we would say that it is the amount of heat that is required, joules, per gram of a substance per degree Celsius that we want to increase. And as it turns out through experimentation, we know basically exactly what water's specific heat capacity is. It comes to 4.184 joules per gram per degrees Kelvin. And this unit is so important that we actually give this conversion factor a name: the calorie. You may recognize the word calorie as being used as a measurement of energy that food contains as shown on nutritional labels, but the way we use this in thermal chemistry is a little bit different. On that note, we can take a look at a sample problem in terms of showing how to use a substance's specific heat capacity in order to do a fairly simple calculation. So if we consider a 50-meter Olympic-sized swimming pool, the capacity of a swimming pool is about 2.5 million liters of water. Don't ask me how I know. Now, if we wanted to do a simple calculation, let's say that the temperature of this pool is 20 degrees Celsius, and we want to see how much energy you would need to add to this volume of water in order to get that temperature to increase by a single degree. Well, if we refer to the specific heat capacity of water, we can actually just multiply a bunch of numbers by that in order to find the amount of energy specifically. So the way that the unit that we use to represent heat is the variable Q in chemistry. And again, if we use the specific heat capacity as a reference, 4.184 joules per gram of the substance that we're increasing the temperature of per degree Celsius, all we need to do is multiply our specific heat capacity by the mass of the water in this swimming pool and by the number of degrees we want to increase the temperature by. Well, we know that we only want to increase the temperature of the swimming pool by 1 degree. So if we multiply by 1 degree Kelvin, that cancels out the temperature. And now we get to the more problematic calculation of, well, what's the mass of this amount of water? Well, we know that this amount of water here, so 2.5 times 10 to the 6 liters of water, we don't know what the mass of this is. However, we do know water's density is approximately equal to 1 gram per milliliter. So if we quickly convert liters to milliliters, we know that 1,000 milliliters per 1 liter, and then we can use this conversion factor of 1.0 grams per 1 milliliter in order to cancel that out here. And if you multiply this into your calculator, because again, we see grams is in the numerator and the denominator here, if you multiply all of this out, because joules is the only unit that we have left, that will tell us the amount of heat that is needed in order to increase this mass of water here by 1 degree Celsius or 1 degrees Kelvin. And if you multiply it out, this comes to exactly 1.046 times 10 to the 10 joules. Now, because this number is very, very large, we typically use a different measurement or a different order of magnitude to measure the amount of heat, the kilojoule. So just like with kilograms, how you have 100 grams per kilogram, a kilojoule is simply 1,000 joules. Sorry about that, I misspoke with kilograms. So if we do this measurement here, and then if we remember that our final answer is only going to have 2 significant digits because of our answer here, that comes to approximately 1.0 times 10 to the 7 kilojoules of heat is required. Now, if we look at basically what we've done in this calculation here, we see that all of this, it looks more complicated than this is, but all that we're doing is trying to find the mass of water here, and this temperature here is the amount that our temperature changes. So from this calculation here, we can actually derive the formula Q, the amount of heat, is equal to the mass of the substance we're adding to times the specific heat capacity in joules per gram per degrees Celsius or Kelvin times the change in the temperature that we want. And with that, that is our first and most important equation that we're going to be looking at in terms of specific heat capacity. And in subsequent videos, we'll look at how to use this in more chemistry-specific contexts.